Hello everyone, welcome to the last lecture in our series on mathematical concepts. I hope you've had fun and been engaged with trying to improve your mathematical confidence and capabilities, and that's what this course is really about. You'll notice also that we've put up a 8th lecture, just some slides, because we're not having an 8th one because you'll be on prac. So that's in the Learning at Griffith site as well. So today we want to look just about problem solving in general. So I'm going to give you a couple of frameworks and ideas, and this is both for yourself in your own problem solving and your own mathematical competence and confidence, but also it will be useful for you as you become a teacher. Now there are lots of problem solving frameworks. The first one listed up there, the 4-step problem solving framework, is from some work out of Victoria. And you can see it's not really rocket science. The step 1 is to analyse the problem, step 2 to explore a way to do it, step 3 find a solution, and then step 4 reflect and see if that answer seems reasonable. Pretty straightforward, pretty obvious, but a simple one that's useful for you and your problem solving, but also again as you're trying to help children solve problems in mathematics. The second one is a bit older and probably a bit more famous. Polya was a very well-known leader in the field of problem solving and how to encourage and develop problem solving skills, and his steps were understand the problem, make a plan, carry out the plan, and then look back. Sometimes called see, plan, do, check. You might have seen posters like that up in schools and things like that. So we're going to go through the Polya one in a little bit more detail. But again, even if you look at Polya's one, the 4 steps aren't rocket science really. It's just a way of being systematic and organising things. So Polya's first step is called understanding the problem. And this is often a step that's overlooked. That what happens is we get a problem and then we just start running into it head first without thinking too much about it. If it's written down, we need to read it carefully. If it's a verbal one, we need to listen carefully and really think about what it's asking us to do. Because often when we do problem solving, people find a solution is just not to the question that they've been asked to do. So the first thing is to really understand the problem. Understand each part of the problem. There might be bits and pieces that you don't understand. There might be words you don't understand, so you need to look them up or try and see what they make sense. Try to think about what mathematics might be involved. And Polya to this end pose some questions or prompts that you can use. Again, this is not rocket science, but what are you being asked to find or show? And I would usually note something like that down. Is there enough information to find a solution? Or are you going to have to make some assumptions about things? Do you understand all the words used in the problem? And again, remember some words have particular meanings in mathematics that they don't mean in general talk. So, for example, sometimes in maths we ask students to draw a table, and you would have probably seen that joke where there's a picture of a kid is drawn, which is of like a dining room table or something like that. Do you need to ask a question to get the answer? So some obvious questions or prompts to think about for yourself as you approach your problem. And again, that might help you with your assignment that you're doing right now. The second step of Polya's process is called make a plan. Or sometimes, again, if you've seen it on posters in schools, it will just say plan. And often in problems, there's a range of ways of doing it. In fact, almost always there's more than one way to do it. Now, some ways will be more efficient and more productive than others, but it's important that you think first about what are some possible ways of doing the answer or finding a solution. And so rather than just making a single plan in detail and rushing ahead, I would encourage you to look at the problem and think of maybe 2 or 3 different ways you could solve it, and then think, okay, which of these looks like the most efficient one or the best one that I'm going to start with, and then choose that strategy and then try and make sure it's clear. Again, this is a problem often with problem solvers, that they just go headlong into their first idea and they can get a long way down the track before they realise that they're way off track. So just taking a bit of time at the start to understand the problem and then consider the possible strategies and then make a plan. The third step in Polyer's system is to carry out the plan. And that's probably not particularly surprising, but once you've decided a plan of how you can attack the problem and what you're going to do, then the next step is to do it. Now again, this is something we need to make sure we take our time and don't rush in. Sometimes we're so busy trying to get the solution that we rush ahead and we can make mistakes or miss things out. So this is why Polyer suggests taking care and having patience to encouraging persistence and trying to work things out. The idea is if it shouldn't be immediately obvious, you do have to take some time to try and nut out what's involved and how you can get there. Now, having said that, if you're heading down a path and after a while it becomes obvious that this is clearly a dead end, then go back to again that second step where you devise your plan and remember you thought about 2 or 3 ways you're doing it, but maybe you need to start on one of the other ways. Or maybe if you step back, you can see somewhere on the line where you made a decision to go one way where you could have gone 1 or 2 or 3 different ways, and you need to try a different path from there. But the third step is to actually do something. And again, this is a place where often people get stuck. They'll read the problem, they'll see it make sense, they'll make some sort of plan, and then they'll freeze because they're worried that it's not the right thing to do. In problem solving, it's okay to try something and not necessarily be on the right track, and then to go back and start again, or to adjust it somewhere along. What's not useful is to sit there and do nothing. But if you go back and as you go through, if you're noting down what you're doing and keeping a track of your thought processes and your activities, then that's a useful part of problem solving, and that's the sort of stuff we'll expect to see in the second assignment. Even the great problems that have been solved by the most prestigious mathematicians in the world are never easy and straightforward. They always go down a path, come back a little bit, try something else, come back. They might go back to their original one. They might go back to the start and try another tack. It's never just, oh, here's a question, here's my plan, there's the answer and I've got it. And then the fourth step, once you've done it, is to go back and check and take some time to reflect that what you've got makes sense. So some simple things and obvious things to do is, first of all, look at the solution and then go back and read the original question and see if it makes sense. Have you actually answered the question, or have you answered something else? See if in the context of what the question's about that the answer makes sense. So if you've got a question that says something about, I don't know, some child running, and you get an answer of 100 kilometres an hour, then probably that doesn't make sense. So it's a good signal to go back and reflect on some of your steps and see if you can find out where you might have made an error that led to just an incorrect solution, which is obviously not reasonable. But just check for reasonableness. If your solution works, then why did it work, or what didn't work, and where can you find out where to adjust it? Again, this is something that mathematicians do all the time. They don't just keep heading down a path and when they get the solution they write it down and say boom, finished. They always reflect and go back and try and justify and make sense of what they've done. An important thing is then to try and be able to justify your strategy and your solution to others. So to other students in your class, or others, you've got students in the class you're teaching, can they justify it to each other? Can they justify it to everyone? Can they explain it to someone who doesn't really know much about it in clear and obvious language? I would then record the strategies in some sort of form in a notebook, or if it's in a class situation you can share them together, or you could keep it electronically some way, because by doing that you've then got a record of things that you might be able to use again later on. Now again, that's a pretty quick overview of Polyer's problem solving steps, but I hope they might be useful for you, not just as a teacher, but for yourself as you are solving problems. And again, this could be a useful framework for structuring your assignment, because essentially what we're asking you to do is to do some problem solving. And again, as I said the other day, the answer is not really that important. The problems are not life or significant things that in the world. It's more the processes, and what we want to see is a good documentation of the process. You'll notice also on the Learning at Griffith site, there's an exemplar there that might help you as you consider that. Also, what I hope is this week in your class, in your tutorial, or at least actually probably next week, if you bring it along and you, no, actually do it this week, sorry, this is week 7. Bring it along and you'll work through it with some team classmates and with your tutor about helping you nut things out. Because if you share things and talk about what you're doing, you can sort of help refine each other's ideas. Now, problems come in a range of forms, different types. This is by no means an exhaustive list. Most commonly we see, particularly in school context, is when we say problem solving, what we get almost always is word problems. And these require reading and interpretation before solving. Now, interestingly enough, some research has been done on word problems, and what we find is about 50% of the kids who struggle, their main problem is they can't read it. So their math skills might be okay, but they're not very good at reading, or they're not very good at interpreting what it's asking them to do. So if you're going to give word problems, and we tend to do it a lot in maths, problem solving doesn't just mean word problems, but when you do get a word problem, make sure you spend a lot of time helping the students and you yourself understanding what it's about and interpreting what it's asking you to do. We also seem to get a lot of application problems where what happens is we learn some standard techniques and then afterwards we try and apply it. So we might give students a whole pile of questions, or you might have a whole pile of questions or exercises about solving simultaneous equations, and then after you've done 25 of those, the next question in the textbook gives you a question like, in the barnyard there are 25 sheep and chickens, and there's 50 legs altogether. How many chickens and how many sheep? Something like that. The value of these, in my opinion, is questionable, but they're widely used. And we know that the challenge will be, if you've learned some mathematics in an abstract way, to apply it is actually a different skill, and a lot of thought and consideration needs to be given about how the content learned in an abstract way actually relates to the problem solving activity. Often we get routine problems, and these are just really ones, they're not really problems at all, they're just about skill development. I tend to call them exercises. It's about doing rote practice, and there's a place for it in learning mathematics, but if you're doing these things, they should usually come after you understand what you're doing, not before. Sometimes you'll get non-routine problems, and some of the ones we've given you in this assignment are non-routine problems, and that means you to think laterally and creatively about what's involved. Often these things don't give you all the information, and you have to try and fill in the gaps or make some assumptions. And if you do that, then you need to write down what those assumptions are and make sure they're reasonable. And then the last sort of problem in this list anyway is multi-step problems, where there's more than one thing to do. And for many of you, these will be proved to be quite difficult. But really, it's important that we start by analysing the problem statement and then look at what the first step might be and trying to think about where we need to head. Again, these really involve logical and sequenced processes, and doing it in a structured way and keeping a track of what you've done, because sometimes when you get down a multi-step problem, you might have to go back a bit and then try again a different way. If you haven't recorded it carefully, then it's difficult to go back and then move down a different path. You either get stuck on the one you're on, or you have to go right back to the beginning. Now, I've just put a few more notes up on these. These slides, of course, will be available in Learning at Griffith, and this is more for your own information, not that I'm going to read them all out to you now. I'm sure you'd love me to do that, but so this is sort of comparing routine and non-routine problems. So routine questions don't really require any higher order thinking skills. They're just clear procedures. And the most obvious one of that is like an example in the textbook, which I'm sure you've done millions of. But non-routine questions, which I would encourage you to do yourself and then encourage you to use as teachers in classes to teach a whole pile of mathematical content and practices. They require higher order thinking, they require people to reason and to make sense of things, and it's much more akin to the sort of things we would use in what we call real life. And there's just some examples of what a routine problem might look like. Find the perimeter of a rectangle with a length 13 and a width of 5. Then the way to do it is really straightforward. There's only really one or two ways you can do it, and in essence they're both the same. And these sorts of ones, you either know how to do it or you don't. There's no figuring it out. If you know how to do it, you'll just quickly do it and you're finished, and if you don't know how to do it, you'll probably put your hand up, look up the answer in the back of the book and copy it out, or ask your neighbour or something like that. So they serve a purpose, but really they shouldn't be as predominant as they are. And I hope that a lot of you who may have been put off mathematics in the past because you saw it as just a whole pile of routine problems that had no meaning and no purpose will rethink these, particularly as you go on to become teachers. And whereas non-routine problems require much more deeper thinking, but they also require a lot more of you as a teacher. And this is one of the main reasons we want you to be doing courses like this, where you develop your own mathematical skills and knowledge and attitudes and values, so you can engage in these non-routine type problems with students in school, because this demands a lot more of you. If we stick to routine problems, we're pretty clear about what's involved and we can keep it contained. If you do non-routine problems, you're going to get more difficult questions from students about what to do. And if you're not confident in your own maths, you'll tend to panic or avoid answering them. So this is why it's important you are strong in your mathematics, so you can deal with these things as they arise and have confidence to help the students along the way without just telling them the answer. Now again, I've listed some of the benefits of non-routine problems. Again, you can read this at your leisure in the slides that will be provided. But when you're doing these, one of the things, it's normal to feel uncomfortable and even frustrated or annoyed about not making progress or getting stuck or something like that. Having emotions is a part of maths, and we know that most kids, including possibly some of you, finish school hating maths or think it's a waste of time. So rather than just pretending that this doesn't happen, what we need to do is actively try and work in class to acknowledge the learners and the students' emotions, and then say, how can we help around it? What can we do? What do you do when you feel uncomfortable or you get frustrated? How can we press on? What are some steps you can take to help resolve the problem so you don't get stuck and frustrated and give up? And that's why it's important to have good communication skills, both yourself as a problem solver, but also yourself as a teacher of problem solving and mathematics. I'm just going to give you a few examples. Now, having said that, I don't necessarily think these are great examples. I've chosen them because they're ones that I commonly see. So here's one. 3 containers have capacities of 3, 5 and 9 litres respectively. How can we use these 3 containers to measure exactly 7 litres of water? Now, if you gave me that problem, I'd probably say, well, who cares? Just look at the markings on the side of the big one and measure it from there, because on the picture you can see it's got markings. So I would try and avoid questions like this, these sort of puzzly things that have no real point or purpose. I would try and find things that are much more interesting and relevant for the students around me. And if I was going to do this, I would try and have some containers rather than just a picture of the containers, and let the kids play with the water and see what they can do, which of course can be a recipe for disaster in the classroom, so you may or may not choose to do that. But that's an example of a non-routine problem that I often see, and if you could use that if you're teaching students about measurement and particularly capacity. But I would try and choose a different one. But again, that's commonly ones we see. Here's another one. A batch of cookies can be divided into equal shares amongst 2, 3, 4, 5, 6 or 7 people with no cookies left over. What is the least number of cookies that the batch could have? And again, you might say this is a bit meaningless, and I would agree. But maybe it could be, you could put a context around it. You know, we're having the school gala day and we want to make some cookies up to sell to make money or something like that, which might make it a bit more relevant for the students. I just want you to be careful that you don't provide questions to students and they go, see, maths is just made up stuff that's got no relevance. It just seems pointless. But these are the sort of things you commonly see, and sometimes what you need to do is take them and try and turn them around so they make more, not more sense, but they are more interesting or more relevant to the student. So if you look at that, what would be the underlying concept? Where would you use it? Okay. So the underlying concept here is about least common multiples, which comes in the number strand. And to do that, you could start going through the multiples of the largest number, which in this case is 6. So you'd go 6, no, 5 doesn't go, 12. Okay, so, and then you might start like that, and you might want to go through all of them till you get to 60. But you might say, well, if 6, we're going to go for multiples of 6, but it also has to have 5 to go in it, which means it has to either end in 5 or 0. So therefore I can skip straight through to 30, but 30 doesn't work because of the 4, so I'd go straight to 60. So you can see the least productive way of doing it would be to go through all the multiples of 6, which are listed there on the third line of the solution. But you might then use the 5 to try and find a more elegant or a quicker solution or something like that. Again, it's an example of a non-routine problem. And then from that, you could build up the idea of least common multiple and help them see that in an abstract way so they could apply it somewhere else. Oh, here's another one we see a lot of. One of my great favourites, not. There are 18 animals in a pet store. Some are birds and some are dogs. And there are 50 legs in all. How many birds and how many dogs are there? And again, my answer to that is usually, well, who cares? Why don't you just count them? But again, what's this one about? And what's the issue? Well, the issue is, again, it sounds like one of those questions that a mathematician's made up for the point of teaching maths, but has no point other than that. But the mathematical concept here is usually simultaneous equations. The problem with this one is if you solve it with simultaneous equations, it's probably not the best way to do it. A guess and check is a more efficient way of doing it. So you're actually teaching the students to be less mathematical. Here's another problem. You can try this one out for yourself. Make a square which is 8 by 8 and cut it out in these proportions, and then rearrange it to make that shape there. And then the investigation is the 8 by 8 one has an area of 64, but the 5 by 13 one has an area of 65. So where's the extra square come from? And that one I think is quite fun, and kids have had a bit of interest and enjoyment in trying to understand it and trying to work out why one square goes missing or one square appears. So here for me would be a better example of a real life problem than some of those ones we said before. And again, I've just made this one up, but it was one that was relevant when I was teaching in a school. There was concerns about the impact of school students' backpacks on their physical health. In other words, the weight of the backpacks on their backs. So the investigation was about how heavy is your backpack, how heavy on average is the student's backpack, what are some of the considerations that need to be involved. Now this is a real life problem which would be much more interesting and relevant for the students to solve, at least it was in the context where I was, because the students were worried that they were carrying around all their textbooks, but then they had to have their devices as well. My view was that the device should take the place of all the textbooks, but no, the school decided that the kids had to have the textbooks and the device, and so their backs were nearly breaking off because it was so heavy. So here's some assumptions and considerations. Is every day the same? All right, so on the phys ed day, these kids had to also chuck in their shoes and their PE uniform because at this school they were required to get changed. Are all the books the same? Does it depend on what subjects you take? Is it different for different days? What if you do music and you've got to carry in your trombone or something like that? So there's an investigation, a real life problem that I think would be much more interesting. Now in this week's workshop, you'll spend most of the time working on your second assignment. So what I want you to do is bring along what you've already done, and I want you to be able to share it with some of your peers in your class, and then give each other some feedback and help each other along the way. This is not cheating, this is the way mathematicians work. They share ideas, they ask for feedback, they question things, and then help each other move along. So thanks for coming into the course. I hope it's been useful for you. I hope I get to see you along the way in some of your other maths education courses. And goodness knows, if you're ever on campus, we might even run into each other rather than just on these video recorded lectures. If you need to, there's some references where those two frameworks came from. All the best.